Just wanted to thank everybody for joining us today for our webinar. Really excited for you guys to be on board with this talk. And without further ado, so this is brought to you by NIRx. So we're in the manufacturing industry, sales support for fNIRS devices, supporting researchers like yourselves over the years. Yes, providing instances such as this webinar is a demonstration of basically our support to the field. We'd like to connect with you. These are the various ways that you're welcome to do so. And we have a newsletter that you're welcome to subscribe to as well. This gives you the latest product features and releases, featured user research, and then exciting news in the field and developments. I just wanted to remind everybody that you're muted. Questions are welcome at any time. Feel free to use the Zoom chat to submit your questions. These will be addressed at the end of the talk. After this concludes, we'll have content available on our website. You're welcome to check out, of course. If you have any questions, you can reach out to us at consulting@NIRx or support@nirx.net. So just introducing myself. So I'm Eric Nelson, technical consultant here at NIRx. I'm joined with Cami as well. That's our marketing and event coordinator. She's helping with things behind the scenes here and organizing this. Yes, so Jessie Fu is our featured speaker. She has training in developmental cognitive neuroscience with overarching research goal to study the impact of early vulnerability in the development of attention functions and its association with socio-emotional adjustments. Her research focuses on implementing a variety of measurements. These include fNIRS, fMRI, to assess how children process social information in different contexts. The ultimate goal of her research program is to contribute to the understanding of child development and improvement of children's socio-emotional well-being. Without further ado, I'm going to hand things over to Jessie.
Thank you, Eric, for the introduction. So I'm starting to share my screen now. Let's see. Okay, you can see the screen fine, right? Okay. So today I'm presenting the devfOLD toolbox. So this is a toolbox for designing age-specific fNIR channel placement. So if you can search the paper already. So this is published in 2021 in Neurophotonics. So I'm taking this opportunity to introduce an extended version of this toolbox. So there I'll go into a bit later. So we basically included data from more age groups. So first of all, I would like to thank my mentor and collaboration, Dr. John Richards. So this project couldn't be done without his neurodevelopmental MRI database, and he also contributed in the computations on channel sensitivity that used in the toolbox. And also, I would like to thank the support for NIRx, because we essentially built this toolbox from existing fOLD toolbox that NIRx developed, and then we use their source code and then extended to more age groups. So first of all, let's talk about the state of the issues that we consider when we conduct NIR or fNIR research. So coming from a developmental background, so when we collect fNIR data in children, we often don't use full head coverage. So for example, we have the 8 source detectors or 16 source detectors. So normally as a developmental researcher myself, need to decide what the montage that I'm gonna use basically the location of source detector placement based on the region of interest that I'm interested in measuring. And also, this is before data collection. Also, after we collect data, we want to know what are the brain regions. Like we see some activation in some channel location, and then we're interested to know what are the corresponding brain regions that is related to. So in order to have an accurate information about channel location and its correspondence to underlying region of interest or ROI, we need to construct MRI head models, and then the most accurate information would come from your participant specific MRI. However, collecting MRI from our own young participants kind of is not often practical, and then defeats the benefit of using fNIRS. So basically, the toolbox is mainly addressed the first issue about designing montage, and then it's also kind of informed the second issue as well about the channel to ROI correspondence. So we all know that when we record fNIR data, we shed light from the source location, and the light would travel through the head and brain tissues, and then we measure the optical intensity at the detector location. So essentially, we need to know basically how this infrared light interact with different head and brain tissues. So in the picture presented on the right is basically, I'll come back to this again later, but this is a visualization of the channel sensitivity profile. So you can think of as the sensitivity means that the extent our instrument can sample the underlying brain region. So basically, I said we need to consider the interaction between the light and then also the optical properties of different head and brain tissues. And then we know that there's a lot of age-related development in our brain structure. So as an example figure here, I show our gray matter and white matter and other matter, the development from newborn all the way till 89 years old. So here to highlight is that there are exponential development in the first 2 years in our brain tissue. And also interesting to know that the brain matter start to decline, the volume start to decline as we get older, when we reach to 70s and 80s. However, our actual head size doesn't really decrease. So basically then it's creating more volume of other matter. So essentially the volume of our brain matters change throughout development. And it's also to show that the sensitivity profile, because that related to how the light interact with the biological brain tissue, that can also change throughout development. So I'm showing this figure is a little bit contain different part of information that I can walk through. So if you just focusing on one of the boxes, you can see this is also a plot of the channel sensitivity profile. And then on the y-axis, you can think about as like intensity, the strength of the light, and then on the x-axis is basically the depth of the tissue. So as a graph presentation on the right, basically the light, as they travel deeper through the brain tissue, the signal reduces. So that's why you can see this shape of line here. So basically when you look across different boxes, one information here is that the sensitivity profile change based on the source detector distance. And also the different lines presented in the graph are different age groups. So hopefully it's obvious to see that when we look at the youngest group here, so from 2 to 6-year-old, their sensitivity profile are different from the adult group, the olive dark green line. And then you can also see that the red dotted line for the adolescence group is almost overlapping with adult age. So here we basically can see that really the younger group from 2 to 6, they show different channel sensitivity profile compared to adolescents and adult group. Here is again to show this is just example MRI from individuals that came from this 4 age group. This is another just a presentation to show that this channel sensitivity profile, which would determine the mapping between channel location to ROI, this profile change across age. So there are existing tools available for designing montage or determining the correspondence between the fNIRS channel location and the underlying ROI. So this is just to list 3 of them, existing tools. So here I need to highlight that all of these tools, they use adult head model as a default. So you can change the underlying head model, but then however, when you just downloaded the tool, it will use an adult head model. And from the slides I showed before, it basically putting a question mark on whether we can use the information from adult head model to if you have a developmental subject. So that's basically inspired our goal to basically modify one of this toolbox, specifically the fOLD toolbox, originally developed by NIRx group, to basically take the toolbox structure, but then add information to different age group. So our goal is basically to create this tool that gives age-specific information about the correspondence between the channel location and the underlying ROI. So for the next slides, I will take you through kind of the basic procedures of the background computation behind the toolbox. So this is to show an overview of the processing pipeline. So in general, there are 3 stages. So first we do the head model construction, next followed by doing some simulation and compute channel sensitivity estimation. And finally, we compute the channel specificity, which is basically the dependent variable going to this toolbox. So just taking you guys to the 3 steps one by one quickly. So the first step, as I said, is to constructing the head models, because we need to know what kind of, things inside of our head. So first of all, we did, this is basically just a general standard MRI processing. So we did a segmentation where we segmented 9 to 10 different tissues based on the age of the head model. So this is basically taking an MRI either from individual MRI or from an average template. So this is basically to annotate inside of the MRI the different tissue types. And then we also did an atlas tessellation. So this is basically to construct the different ROIs based on different developmental appropriate atlases. So then on the scalp level, we also need to co-register the probe location. So the commonly used template would be the 1010 location and 105 location. So we co-registered both the 1010 electrode location as well as 105 electrode location on the MRI head model. So the second step is doing simulation and compute sensitivity. So as I said in the beginning, we need to model how the infrared light travels through the head. However, it's difficult to do an in vitro experiment when you literally shine a light through a living human. So that's why we would rely on computer simulation to do that. Basically, to provide a model on how the light travels through our head and brain tissue. So to do that, we use the Monte Carlo simulation. So basically for all the 10-5 electrode location, we shoot light through them. So we model how photon travel through the tissue structure. So in the simulation, we launch 100 million photons from the 10-5, each of the 10-5 electrode location into the already segmented MRI to model how the light travels through different brain tissues. So then we have an output of all of those voxels inside of the head. So model after the fold toolbox, here so there are a lot of possible channel combinations. So we reduce our solution space to 130 selected possible thousand detector channel combination. So for this 130, we basically need to compute the source detector channel sensitivity. So we use this formula that published in this +1 paper. So basically, by computing channel sensitivity, you multiply the fluence value at the detector location times the fluence value at the source location. So this value is computed at each voxel inside of the head. And also we normalize this sensitivity value such that we divide the product to the fluence of the whole head. So I showed the formula here. So essentially the outcome is the sensitivity at the channel location relative to the sensitivity of all voxels inside of the MRI volume. So this is a graphic presentation of this sensitivity profile this normalized sensitivity profile we computed. So again, this is an example head model from the 3 age groups. So you can see also visually the sensitivity profile look different across the 3 head models in different age group. So taking that calculation, we computed the brain sensitivity as well as our ultimate outcome variable. So basically, this is the outcome is the channel to RI sensitivity that is included in the toolbox. Basically, this is the index of the percentage sensitivity of the channel location to the given RI out of the total sensitivity of the channel to the brain. So here I will go repeat it again when I go into the toolbox. So we provided 3 type of channel to RI specificity calculations you can see from the toolbox. One is that we compute that from an average template in a given age. And then the second is that you can compute this using an individual MRI, so from a given participant. And we also provided an averaged value. So for a specific age group, we have a number of our MRIs, say 20 MRIs. So then we computed this value for each MRI and averaged them across the MRI volume, the head model within the age group. So we provide kind of 3 type of computation. So I'll now kind of go into more of the demonstration of the toolbox. So first of all, I'll give you a quick overview of what is in the toolbox, and then I'll exit out of my presentation to give you more details of how you navigate in the toolbox. So here I provide the GitHub link where you can download the toolbox. So essentially, when you go into the toolbox, you can select the age group that you are working with, and also select from the 6 type of development appropriate atlas. I normally using the Lonely or the LPBA atlas, but you can choose your own, depends on your preferred atlas passellation. And then within each atlas, then it listed different ROIs you can select. So you can pick one, and then you can select the specificity threshold. So basically, kind of the higher is basically better sensitivity to this given ROI. So the default value is 30. So I normally would set above 15 or 30. But you can, this is also user specified free parameter you can experiment with. And then the force asymmetry option is when you basically doing both left and right hemisphere, and then it's gonna give you the force to have the same layout. You can also, so the last slide is on this 1010 tab. So it gives you the 1010 presentation, and then you can click on the summary slide. So here is really handy, give you the snippet of the lookup table. So it has the source location and also the specificity. So you can also toggle through the tab on the top. So then for this one, it gives you, for the channels tab, it gives you the channel to ROI correspondence so for each given channel, what are the ROIs is sensitive to. So I'm gonna exit here to show you more specifically how you navigate within the toolbox. So here, so when you download the toolbox, so this is I downloaded from the GitHub. So in the lookup tables folder, you will basically see a bunch of Excel file have all of the information going to the toolbox. So basically it has all of the possible 130 channel locations, as well as all of the ROI and correspondence information. So the lookup table is the full information, and then the toolbox basically just giving you a convenient visualization of the lookup table. So the separate age group folder will contain all of our computations of all of our age group. So on the GitHub, in our first version of the toolbox, we shared all of the infancy age, as well as 4 years old, 12 years old, as well as 20 to 24 years old. And since then, we basically computed more of the age group. Now we have full coverage from the infancy age, childhood age, adolescence age, and adult age. And then we starting to compute the older adult age. So at the moment, we only have 85 to 89 as a demonstration. So basically, all of the you can send me a request email for the additional age group that you cannot download from GitHub. So this folder would contain basically the data for individual age group. So before running the toolbox, I would basically include all of this devfOLD folder into the MATLAB search path. Then I use this command to launch the toolbox. So now I'll show you how you navigate into the toolbox. So in the toolbox, we put some already available age group you can just click through. So the default would be the devfOLD, the original fold data. So the default basically is the original fold toolbox. then we provided the 3 months, 6 months, and adult. So you can click one and then select the atlas and then select ROI, so it will show you all of the channel locations. And then, so in the summary, I showed again, so here it shows the thousand detector locations, and then their specificity to this frontal ROI. And then when you click into the channel, it shows the channel to ROI correspondence. The south detector is also just another information tell you kind of the thousand detector the names that involved in that sensitive to the frontal ROI. So when you need to go into a customized age, so the age group not in this dropdown, you will set this back to default and then type in an age group that showed age name that showed in this separate groups folder. So for example, I'll do the 80 to 89 years old. So I'll just 85 to 89. So I'll type into this name. And then when you hit enter, it would refresh. So we can do another demonstration. So the same thing, I'm gonna go back to the 1010. So you can change these parameters around. So it's basically give you the 1010 layout and summary. And then another handy structure like function here is that you can save and export the data. So when you click on save, it's going to my other window. I'll move back here. So it's basically gonna save .mat data structure about this montage. So this is really handy that you can, if you have subsequent MATLAB processing streams, so it's good for integrate with those. So for example, I can use this source location information to further co-register the location on the MRI. So basically it's convenient for you to integrate this procedure to your subsequent MRI MATLAB processing stream. So if you're not using MATLAB, you can also do the export function, so that can save your information you see from the toolbox to a Excel or text format. So here conclude my basic demonstration. So I'll go back to my slide and continue. Okay, so here I'm just showing the next few slides. I would just like to show you that the data, some data visualization come from the data from the toolbox. So here we plotted out the example age group that we included in the toolbox. So this is the 6 months, 3 months, 6 months, 20 and 24 years, and then the fold adult head model. So we plotted out the number of channels with specificity value larger than 1%. And then this is all of the ROIs in the LPBA atlas. So here the key information is that it confirms that fNIRS cannot really tap into deeper tissues. For example, it's not really good measuring fusiform gyrus. You have really low sensitivity value across the board. And also locations such as insular cortex and orbital frontal gyrus. So it just shows that NIRS is really not really good into tapping into those deeper areas. And then we also want to see what is the extent of our age-related consistency and differences. So here we pick an example ROI. This is the left inferior frontal gyrus from the LPBA atlas. So here we set the specificity threshold to 15%. So here you can see that if we do that, essentially the devfOLD toolbox will show that you have the same montage across all of this age group. So for this ROI, we apparently have across age consistency, and you don't really need to worry about having different montage for different age groups. However, so this is basically 3D presentation on the layout. So this is just co-register the source detector location on an adult head model. But you know, this is to show that this kind of montage would apply to all of the age groups that I showed for in the previous slides. But however, if we pick another ROI, so in this case, the left superior orbital gyrus, here you can see that we have a cross age difference when we set the specificity value to 15%. So then basically the toolbox will show that we have different montage across for all those different age groups. So here I showed it in a 3D presentation. So you can see that the 3 months, 3 years, 6 years, 12 years adult and older adult, they don't have the same layout. However, it seems like the 3 months and older adults have the same layout. So there's just to show that there's both across age consistency as well as differences. So in the final point, I would like to highlight the applications for this toolbox in terms of conducting fNIRs research. So first of all, I would like to highlight this that fold toolbox or our extended devfOLD toolbox is really basically provide a convenient tool for designing age-specific montage based on your participant age group as well as the ROIs you're interested in. And then we can conveniently do this before we start collecting data. However, so there is no straight answer about whether there is an age-related differences or consistency, because from the demonstration, you probably can already see that the across age differences on the montage would depend on the atlas and ROI you pick, as well as the specificity threshold you set. So for example, if you're picking a large ROI, and then if you set your specificity threshold really high, sometimes you do see there is actually a cross-age consistency. So maybe that if you collecting data from a wider age group, for example, across from younger children to adolescents, and then if you do not want to change your montage, then you can consider using a larger ROI and then using a higher specificity threshold. And then the toolbox basically giving you a tool to evaluate yourself whether you can keep the same montage or whether you need to change your montage based on your different age groups. And also, basically, the toolbox provide a procedure. You can actually replicate this procedure on a subject-specific MRI. So basically, you can collect MRI from your own participant and then use the method behind the toolbox and then determine most accurately for your own participant, for this specific participant, where you would put what is the best configuration to measure the ROI. Also, however, I would also like to highlight some limitations. So one of it is that it has constrained solution space, which means that we basically only picking possible channel combinations from the 130 possible 1010 channel configurations. So it doesn't really go anywhere on the scalp surface. Also, you can see that it's only consider ROI one by one, so it's not really convenient if you have multiple ROIs and then you want to design a montage that tap into a list of ROIs you're interested in. So it doesn't really provide information of the combined specificity for multiple ROIs. So this basically conclude my presentation, and thanks for your attention, and I can take some questions on the remaining time.
Okay. Yeah, thanks so much. No doubt a labor of love for the fNIRS field. I can't imagine how long this took you to compile.
Yeah, the simulation took a while.
Yeah, so we're going to open this up to questions. And we do have a few. There's a few received during the registration process. So I'll just go through these. So is there a specific age range where age-specific optoid placement is most valuable?
Yeah, so let me somehow I exit out my presentation. Yeah, so again, as I said in the last slide, that it depends on depends on, of course, the age group and also the ROI you're interested in, how large the ROI, and then also the specificity value. But just to highlight, this is the data from one of our published paper. So from couple published paper from me and Dr. John Richards, we found that the infancy and also younger age group from 2 to 6, they are most different from the default adult head model. However, I would not really just have a blank conclusion, but really I want to highlight that the toolbox is basically provide a tool for you to evaluate the age difference for yourself. So, I would encourage you kind of click into the toolbox, look at our data in the toolbox, and to see whether there is an age difference for the age group you're interested in and your ROIs.
Okay, thank you. Let's see what's next here. And yeah, is there an objective method to choose the specificity value? If not, what value would you recommend?
Yeah, that's good question. So there's from the fOLD paper as well, we don't see an objective way of choosing it. It also depends on the ROI. So when you have a larger ROI, for example, if you do like the low bar atlas and then you choose frontal, you can see that if you just put in the default 30%, you will see a huge coverage, which you probably you don't need that huge coverage, or you simply don't have that many thousand channel sensors. So it's basically depends on the coverage and the number of sensors you have, and also so then with those kind of large ROI, you would want to put the threshold higher to be more selective. However, if you use more fine-grained pixelation, if you're interested in a more smaller ROI, you probably want to reduce it lower because the sensitivity for those, the value range would be on the lower side. So it's also dependent on the atlas and ROI you're selecting, and also your available source and detector sensors.
Okay. Let's see what's next. How would you account for the suggested 2 centimeter channel spacing and 3 centimeter channel spacing when utilizing the same montage measuring from a 1-year-old and an adult, for example?
Yeah, this is a great question. So in our limitation slide, so if you see the toolbox, let me pull up the slide. So the quick answer is that we do not taking account into varying distance because, as I said, the solution space, our possible combination are fixed. So we only consider the southern detector are on the adjacent side. So from our computation, we believe it's generally about 2 to 3 centimeters, but then again, we do not really taking account, making sure you cannot really set a distance in the toolbox.
Okay.
And then the distance are fixed. You cannot really change it in the toolbox.
Okay. Yeah, so just two more, it looks like. I'd like to learn about ideal configurations for whole brain head coverage with 24 channel system. Yeah, so for this individual, feel free to reach out to us at support@NIRx.net. A few more details might be helpful for us to kind of consider this with you. And then the last question, do you use any other technologies to identify the most appropriate positions for placement? Okay, sorry. Not entirely sure the technologies that they're referring to, but
Yeah, so one way answer this is I showed other available tools. So for example, the array designer is kind of a little bit more more complex than the fold or devfOLD in the way that it allow you to actually for this one it takes into different distance and then also the number of cells and cells detector you have. So this is using a more complicated algorithm behind it and allow more customization, but again, you would have to adapt it to like age specific or participant specific head model. So however, I think so the alternative way I would suggest is basically using the procedures I introduced for fold and devfOLD in this talk. So this procedure can be adapted to use basically your participant specific head model. So that can be the most customized or accurate to your own participant data.
okay. All right. Yeah, once again, we really appreciate you joining us. And yeah, for all of you as well. And I guess tune in next time for, I think we have another webinar coming up here very shortly, but always visit our website to see, the list of webinars that we have in the queue. So thanks again.
Thanks, everyone. Thank you, Eric and Cami, for hosting this. Bye.